Is there a wall at the end of everything? A final frontier where the universe simply stops? Subscribe and join us on this journey into the unknown. For all of human history, the sky was a simple ceiling, a familiar, comforting dome sprinkled with the gentle light of wandering gods and fixed stars. It was a finite space, knowable and contained. We lived in the center of a cosmic fishbowl looking out. The stories we told, from the Babylonian astronomers charting the heavens on clay tablets, to the Greek philosophers envisioning celestial spheres nested within one another, were all attempts to map the edges of our container. The universe had boundaries, and we were safely tucked inside. This idea was not just science. It was a deep, psychological comfort. It gave us a place, a sense of cosmic orientation. But science is the engine of uncomfortable truths, and in the early 20th century, it began to dismantle that comforting ceiling, piece by piece. The revolution didn't start with a bang, but with the quiet, meticulous work of astronomers who were simply trying to measure the heavens. They built larger and larger telescopes, instruments of glass and steel designed to gather the faint, ancient light from the farthest reaches of the night. One of these astronomers was a man named Edwin Hubble. In the 1920s, from his perch at the Mount Wilson Observatory high above a young Los Angeles, Hubble was engaged in a debate that consumed the astronomical world. He was studying faint, spiral-shaped smudges of light called nebulae. Most astronomers believed these were nascent solar systems forming within our own Milky Way galaxy. But Hubble, using the most powerful telescope on Earth, was about to prove them all wrong. He painstakingly measured the distances to these smudges, and the numbers he calculated were staggering. They were not inside our galaxy. They were millions of light years away. They were entire galaxies themselves, island universes of billions of stars, adrift in an ocean of darkness far vaster than anyone had ever dared to imagine. In a single stroke, the known universe expanded 100 billion-fold. Our cosmic fishbowl had been shattered, but this was only the first shock. As Hubble continued to observe these distant galaxies, he found something even more profound. Something that would tear down the very foundations of cosmology. He noticed that the light from these galaxies was stretched, shifted towards the red end of the spectrum. It was the cosmic equivalent of a siren's wail dropping in pitch as it speeds away. The conclusion was inescapable. Almost every galaxy in every direction was rushing away from us. The universe was not a static, eternal stage. It was expanding. And if it was expanding, then it must have been smaller in the past. Smaller and smaller and smaller, until you rewind all the way back to a single, infinitely dense point in time. The universe had a beginning. We call it the Big Bang. This discovery gave our cosmos a history, a birth certificate written in the light of fleeing galaxies. But in doing so, it unleashed a question that haunts us to this day. If the universe had a beginning in time, could it also have an end in space? The idea of an expanding universe, born from a singular moment, immediately forces a difficult question. If you could ride a spaceship faster than light, traveling in one direction for billions of years, would you eventually hit something? A wall? A final boundary marking the edge of existence? Our intuition, forged in a world of walls and fences, screams yes. Everything has an end. But in cosmology, intuition is a notoriously poor guide. The first boundary we must confront is not a physical wall, but a curtain woven from time and light itself. It's called the observable universe. The concept is both simple and profoundly difficult to grasp. When we look out into space, we are also looking back in time. The light from the sun takes 8 minutes to reach us. We see the sun not as it is, but as it was 8 minutes ago. The light from our nearest neighboring star, Proxima Centauri, takes 4 years. The Andromeda Galaxy, our closest galactic neighbor, appears to us as it was 2.5 million years in the past. As we peer deeper into the cosmos with our telescopes, we are seeing light that has traveled for billions of years to reach us. The universe is approximately 13.8 billion years old. This means that any light from a source farther away than 13.8 billion light years hasn't had enough time to reach us yet. This creates a perfect sphere of information around us, a cosmic horizon. The current diameter of this sphere is about 93 billion light-years across, a figure made larger than our simple calculation because the universe itself has continued to expand while the light was traveling. Everything inside this sphere is the known, observable universe. Everything outside of it is, for now, completely unknowable. It's crucial to understand what this horizon is and what it isn't. It is not a physical edge. It is not a point where stars and galaxies suddenly cease to exist. It is purely a limit of our vision. A boundary of information imposed by the finite speed of light. An alien astronomer in a galaxy a billion light-years away would have its own observable universe, its own cosmic horizon, containing parts of the cosmos that are invisible to us. while parts of our sky would be invisible to them. This realization is both a solution and the beginning of a much deeper mystery. It provides a technical answer to the question of where our visible universe ends. It ends at the point where light has run out of time, but it does nothing to answer the ultimate question. What lies beyond that horizon? Is it simply more of the same? An endless, homogeneous sea of galaxies, stars, and planets stretching on into infinity? This is the simplest assumption, the one that many cosmologists lean towards. An infinite expanse of existence, with our observable patch being just one insignificant bubble in a limitless ocean. But what if it's not? What if the universe beyond our sight is fundamentally different? What if the laws of physics themselves begin to change? The observable horizon, a concept born from the simple fact of light's finite speed, forces us to confront the true scale of our ignorance. We are like sailors on a small raft in the middle of a vast, fog-shrouded ocean. We can see the water for a few miles in every direction, and it all looks the same. But we have no way of knowing if, just beyond the fog, the ocean ends in a colossal waterfall, or if it simply continues on forever. The edge of what we can see is not the edge of reality, and the question of what lies beyond it is perhaps the most profound in all of science. The idea of an endless expanse of stars stretching on forever feels like a plausible, if dizzying, answer. But the alternative, that space itself has an end, presents a paradox so profound it makes the mind reel. Let's entertain the notion for a moment. Imagine our spaceship has traveled for eons, past the edge of the observable universe, and we finally arrive at the absolute edge of space. What do we see? Is it a solid, impenetrable wall? If so, what is this wall made of? And more importantly, what is on the other side of it? This isn't a trivial question. It's a logical nightmare that challenges the very meaning of words like outside and nothing. If you could somehow punch a hole in this cosmic wall, where would your hand go? Would it enter a realm of pure nothingness? A void? But what is nothing? In physics, a vacuum is not nothing. It is a seething cauldron of virtual particles popping in and out of existence. True, absolute nothingness, the absence of space, time, matter, energy, and even the laws that govern them, is a concept that science cannot handle. It may not even be a coherent idea. This logical paradox is the first major hurdle for the concept of a cosmic edge. It seems to create a boundary between existence and non-existence, a line that seems impossible to define or describe. But the problem runs even deeper, striking at the heart of a principle that has guided cosmology for a century. It's called the cosmological principle, and it's a foundational assumption for nearly all of our models of the universe. It states that on the largest scales, the universe is homogeneous and isotropic. Homogeneous means it's roughly the same everywhere. No matter where you are in the cosmos, the general distribution of galaxies looks about the same. Isotropic means it looks the same in every direction you look. For a century, our observations have backed this up. The universe, when you zoom out far enough, is a remarkably uniform tapestry of galactic clusters and voids. An edge would shatter this principle. A boundary would, by its very nature, be a special place. The universe would no longer be the same everywhere. The region near the edge would be fundamentally different from the regions in the center. Furthermore, the edge would create a special direction. An observer living near the boundary would look one way and see a universe teeming with galaxies, and look the other way and see the end. This would violate isotropy. The cosmological principle is not just an elegant idea. It's a critical piece of mathematical machinery. Without it, our ability to describe the universe as a single, coherent entity with a single set of physical laws breaks down. The equations of general relativity, which we use to model the entire cosmos, would become almost impossibly complex. The existence of an edge would mean we live in a special, privileged part of the cosmos. A return to the pre-Copernican idea that our location is somehow unique. For most physicists, this is an unacceptable step backward. The paradox of the boundary seems to be telling us that our intuition is wrong. Space cannot simply end. But if it doesn't end, is it therefore infinite? The answer, it turns out, was hidden in the strange and beautiful mathematics of a German mathematician who lived a century before Einstein, and in the curvature of space-time itself. If a physical edge is a logical and physical impossibility, are we then forced to accept an infinite universe? Not necessarily. The answer, strangely enough, lies in geometry, but not the simple flat geometry we learn in school, where parallel lines never meet and the angles of a triangle always add up to 180 degrees. The true geometry of the cosmos was revealed by Albert Einstein in his theory of general relativity, and it is far more bizarre and wonderful. Einstein showed that space and time are not a passive backdrop for matter and energy, They are a single dynamic entity called spacetime, and spacetime can be bent, stretched, and warped by the presence of mass. A planet doesn't orbit the sun because of a mysterious force pulling on it. It follows a straight line through spacetime that has been curved by the sun's immense mass. On the scale of the entire universe, the collective gravity of all the matter and energy within it determines its overall shape, its global curvature. And this curvature dictates the ultimate fate and nature of space itself. There are three fundamental possibilities for the universe's geometry. The first is a flat universe, obeying the rules of Euclidean geometry we are all familiar with. In a flat universe, if you and a friend both traveled in parallel straight lines, you would remain forever parallel. A flat universe, by its nature, would continue to expand, but ever more slowly, eventually coasting to a halt after an infinite amount of time. For all practical purposes, a flat universe is an infinite universe. The second possibility is an open universe, which has what's called negative curvature. Its geometry is like the surface of a saddle. In this universe, parallel lines would diverge, and the angles of a giant triangle would add up to less than 180 degrees. An open universe would also expand forever, and its infinity is even more pronounced. But it is the third option that provides a stunning solution to the paradox of the edge. This is the closed universe, which has positive curvature, like the surface of a sphere. In this universe, two parallel lines of travel would eventually converge and cross. The angles of a triangle would add up to more than 180 degrees. Most importantly, a closed universe is finite, but it has no boundary. It is unbounded. Think of the surface of the Earth. It is a finite, two-dimensional space. You can't travel on it forever, but there is no edge to fall off of. If you walk in a straight line, you don't hit a wall. You simply end up back where you started. A closed, spherical universe would be the three-dimensional equivalent of this. You could travel in a straight line in your spaceship for trillions of years, and you would never hit a boundary. You would simply, impossibly, arrive back at your starting point. This elegant concept solves the problem completely. Space doesn't end, it just wraps back on itself. This presented a clear path forward for science. All we had to do was measure the geometry of the universe. If we found it was positively curved, we would know we live in a finite, unbounded cosmos. If it was flat or open, we would have to confront the staggering reality of a truly infinite existence. The hunt was on, and as our instruments became more and more precise, they began to close in on an answer. Missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and later the Planck satellite, measured the geometry of spacetime with astonishing accuracy by studying the faint afterglow of the Big Bang. And they delivered a verdict that, instead of solving the crisis, deepened it. To within a margin of error of just 0.4%, our best measurements show that the universe is perfectly, stubbornly, impossibly flat. This result, the product of our most advanced science, points directly back toward the very idea that seems so paradoxical: an infinite universe. The elegant solution of a closed, finite cosmos seemed to be slipping through our fingers, leaving us once again to stare into the abyss of endless space. The finding that the universe is flat, and therefore likely infinite, was a jarring conclusion for many physicists. It felt like trading one problem for another. The paradox of a physical edge was replaced by the dizzying, incomprehensible nature of a truly infinite reality. But what if the measurements were hiding a more subtle truth? What if the universe was so unimaginably vast that our observable patch merely appears flat, in the same way the Earth appears flat to someone standing in a field? This idea brings us back to the most elegant and mind-bending solution to the problem of the edge: the finite but unbounded universe. To truly grasp this concept, we must perform an act of mental gymnastics. We have to shed our three-dimensional intuition and imagine ourselves as beings living in a lower-dimensional world. Imagine you are a perfectly flat, two-dimensional creature. Your entire universe is a flat sheet of paper that extends to infinity. You can move forward, backward, left and right, but you have no concept of up or down. If someone asked you if your universe ends, you would say no, it goes on forever. Now, imagine that your flat 2D universe is not a sheet of paper, but the surface of a gigantic sphere. For you, a 2D being, nothing has changed. You can still only move along the surface, forward, backward, left, and right. You still have no concept of up or down into the third dimension where the sphere exists. If you walk in what you perceive to be a straight line, you will never encounter a boundary, a wall, or an edge. But if you walk for long enough, you will experience something utterly baffling. You will arrive back at the exact point where you started. Your universe is finite. It contains a finite amount of surface area, but it is also unbounded. It has no edge. The trick, the secret, is that your 2D universe is curved through a third dimension that is inaccessible and unimaginable to you. This is the proposed solution for our own cosmos. The theory suggests that our three-dimensional universe of space could be the surface of a four-dimensional hypersphere. We can move in our three dimensions, length, width, and height, but we cannot perceive or access this fourth spatial dimension. If this were the case, our universe would be finite. It would contain a finite amount of volume, a finite number of galaxies, and a finite amount of energy, but it would have no edge. If we were to fly our spaceship in a perfectly straight line, we wouldn't hit a wall. We would simply be traveling along the curvature of this 4D hypersphere. After an unimaginable amount of time, perhaps trillions upon trillions of years, we would find ourselves right back in the Milky Way, having circumnavigated the entire cosmos. This concept, known as a three-sphere or a closed toroidal universe, resolves all the paradoxes. It avoids the logical nightmare of a boundary with nothing on the other side. And it explains how the universe can be finite without violating the cosmological principle. Because a hypersphere has no center and no edge, every point is equivalent to every other. It remains the most mathematically beautiful and logically satisfying answer to the question. But it is not the only one. And the other leading theory is even more radical, suggesting that our entire universe is just a single, insignificant bubble in a churning, infinite foam of creation. The flat geometry of our universe, while pointing towards infinity, also presented cosmologists with a different kind of problem. For the universe to be so perfectly flat today, its initial conditions at the moment of the Big Bang had to be fine-tuned to an absurd degree of precision. If the density of the early universe were off by even a minuscule fraction, it would have either collapsed back on itself almost immediately, or flown apart so fast that no stars or galaxies could ever form. This flatness problem was one of the great puzzles of cosmology. The solution came in the early 1980s with a groundbreaking theory called cosmic inflation. The idea was that in the first fraction of a second after the Big Bang, the universe underwent a period of astonishing exponential expansion, growing from smaller than an atom to larger than a galaxy in less than the blink of an eye. This violent stretching would have flattened out any initial curvature, just as stretching a crumpled balloon smooths out its wrinkles. Inflation beautifully explained why our universe appears so flat. But this elegant solution came with a truly radical consequence. The physicists who developed the theory, most notably Alan Guth and Andre Linde, soon realized that this inflationary process might not have been a one-time event. According to their models, inflation, once started, is eternal. It's a runaway chain reaction that never completely stops. Imagine the universe as a vast, rapidly expanding ocean of inflationary energy. Our Big Bang was like one small patch of this ocean suddenly calming down, its energy converting into the matter and radiation that formed our cosmos. Our universe is a bubble of tranquility that has nucleated within this eternally expanding metaspace. But outside our bubble, the inflationary ocean continues to stretch at superluminal speeds, and it will continue to do so forever. And in this infinite churning ocean, other bubbles are constantly forming. Countless other universes, each with its own Big Bang, each potentially with its own unique set of physical laws and constants. This is the scientific origin of the multiverse. It isn't a flight of philosophical fancy. It is a direct, logical extension of our best theory for explaining the properties of our own universe. In this model, the question, does space end, takes on a whole new meaning. Our universe, our bubble, could be finite. It could be a closed sphere, or it could be a flat, infinite sheet. But even if our local universe is finite, it exists within a larger reality, the multiverse, that is truly infinite. Space in this view never ends. It is an endless factory for producing new universes. This theory offers a stunning answer to the fine-tuning problem. If there are infinite universes, it's no longer surprising that we find ourselves in one that has the perfect conditions for life to exist. It's like walking on a beach with infinite grains of sand and finding one that is perfectly round. It's not a miracle. It's a statistical inevitability. This vision of reality is perhaps the most humbling in all of science. It suggests that everything we've ever known, every star, every galaxy, our entire 93 billion light-year wide observable universe is just one bubble in an infinite foam of other worlds. It is an idea that pushes the boundaries of what we can test and what we can ever hope to know. It presents a cosmos where our space might have an end, but space itself goes on forever. We are left with two competing magnificent visions, a single finite universe that cleverly wraps back on itself, a beautiful and self-contained cosmic jewel, or an infinite multiverse, a chaotic and eternal sea of creation where our entire existence is but a single, fleeting drop. The choice between them would not be settled by mathematics alone, but by the very human story of the scientists who dared to imagine them. Scientific theories are not born in a vacuum. They are the products of human minds, forged in moments of brilliant insight, dogged persistence, and sometimes profound error. The story of our understanding of the universe's edge is a deeply human drama, a tale of intellectual titans clashing over the very nature of reality. And it begins with the greatest physicist of the modern age, Albert Einstein, confronting a universe that refused to behave as he wanted. In 1915, when Einstein published his theory of general relativity, he created a mathematical framework to describe the entire cosmos. But when he applied his own equations to the universe as a whole, they gave him a result he could not accept. They predicted a universe that was unstable, dynamic. It had to be either expanding or contracting. It could not simply sit still. This idea was anathema to the prevailing scientific and philosophical view of the time, and to Einstein's own intuition. The universe, he felt, should be eternal, static, and unchanging on the grandest scale. So strong was his conviction that he did something he would later regret for the rest of his life. He altered his pristine equations. He introduced a new term, a fudge factor, which he called the cosmological constant. It acted as a kind of anti-gravity, a repulsive force that would perfectly balance the inward pull of gravity, allowing for a universe that was static and stable. It was a mathematical trick to force the cosmos to conform to his sense of aesthetic and philosophical beauty. He had created a universe that was finite, closed, and eternal, a model that neatly avoided the problem of an edge and the unnerving prospect of a beginning. For a few years, Einstein's static universe was the leading model, but across the ocean, an American astronomer was gathering the evidence that would prove it wrong. That man was Edwin Hubble. Where Einstein was the master of the thought experiment, a theorist who explored the cosmos with chalk and a blackboard, Hubble was the quintessential observer. He was patient, meticulous, and armed with the most powerful eye on the planet, the 100-inch Hooker telescope at Mount Wilson. Hubble was not trying to challenge Einstein. He was simply trying to measure the universe. As he cataloged the distances and velocities of his newly discovered galaxies, the data began to paint an undeniable picture. The farther away a galaxy was, the faster it was receding from us. The relationship was clear, linear, and inescapable. The universe was not static, it was expanding. When Einstein heard of Hubble's results, he traveled to Mount Wilson in 1931 to see the evidence for himself. As he peered through the eyepiece of the telescope that had dismantled his vision of the cosmos, he conceded defeat. He declared that the introduction of the cosmological constant was the biggest blunder of his life. The human desire for a comfortable, eternal cosmos had been overthrown by the cold, hard light from distant galaxies. The universe had a history, and the quiet, determined observer had corrected the brilliant theorist. The stage was now set for an even deeper, more personal struggle to understand what this expanding cosmos truly implied. The intellectual drama that began with Einstein and Hubble was reignited decades later, not by astronomers peering through telescopes, but by theoretical physicists wrestling with the fallout of the Big Bang theory. By the late 1970s, the standard Big Bang model, while successful, was plagued by nagging inconsistencies, like the flatness problem. The universe appeared too perfect, its initial conditions too finely tuned. The search for a solution was on, but it wasn't found in a grand, established laboratory. It was found in the mind of a young, relatively unknown particle physicist at Cornell University, who was about to have the most important night of his life. His name was Alan Guth. He hadn't set out to reinvent cosmology. He was working on esoteric theories about magnetic monopoles, but the equations he was developing seemed to have a strange consequence. They suggested a phase of incredibly rapid, exponential expansion in the early universe. At first, he didn't know what to make of it. The story has become a legend in the annals of physics. On a cold December night in 1979, Guth was at his desk, meticulously working through the implications of this inflationary phase. He suddenly realized that this explosive growth spurt didn't just solve the obscure monopole problem he was studying. It solved all of the major puzzles of the Big Bang at once. It explained why the universe was so uniform, and most importantly, it explained why it was so perfectly flat. In a flash of insight, he saw that any initial curvature of the universe would be stretched into effective flatness, just as the surface of a tiny wrinkled balloon becomes flat when it's inflated to the size of the Earth. In his notebook that night, he wrote the words "spectacular realization" in capital letters, surrounded by a hand-drawn box. He knew he had stumbled onto something revolutionary, but bringing that idea to the world was a struggle. The theory of cosmic inflation was radical, speculative, and to many, it sounded like science fiction. Guth faced intense skepticism from the established physics community. His idea was a beautiful patch, but it seemed to have its own flaws, predicting a clumpy, inhomogeneous universe that didn't match our own. The theory could have died there, a brilliant but flawed idea. But it was rescued and transformed by another physicist, Andrei Linde, then working in the Soviet Union. Linde, a charismatic and visionary thinker, saw the profound potential in Guth's work. He was captivated by the power of inflation, but troubled by its initial form. Working in relative isolation behind the Iron Curtain, Linde developed a new version of the theory, called new inflation, and then later, chaotic inflation. His models were more elegant and robust, but they also led to a far more staggering conclusion. Linde realized that inflation wasn't a one-time event that happened in our past. It was an eternal, self-reproducing process. Once it starts, it never fully stops, constantly spawning new universes from the quantum foam of an ever-expanding metaspace. It was Linde who took Guth's initial insight and followed it to its ultimate, terrifying, and beautiful conclusion: the multiverse. He became the chief evangelist for this new cosmic vision, engaging in passionate debates with skeptics who argued it was untestable, unfalsifiable, that it wasn't science at all. The human drama had evolved. It was no longer about whether the universe was static or expanding, but about whether our universe was unique, or merely one of an infinite number of cosmic accidents. It was a battle fought not with telescopes, but with equations, ideas, and the sheer force of scientific conviction. To choose between a finite, self-contained universe and an infinite, bubbling multiverse, physicists needed more than elegant theories. They needed data. They needed to measure the shape of the cosmos with a precision that was previously unimaginable. They needed to build a tool that could see back to the very beginning of time and take a picture of the infant universe. That tool was not a traditional telescope made of mirrors and lenses, but a series of hypersensitive radio antennas, designed to capture the faintest, most ancient light in all of existence. The hunt for the cosmic shape became a hunt for the echo of the Big Bang itself, the cosmic microwave background, or CMB. This light is the oldest light we can ever hope to see. It was released about 380,000 years after the Big Bang, when the universe, which had been an opaque, superheated plasma, finally cooled enough for atoms to form. At that moment, light was set free to travel unimpeded across the cosmos. For 13.8 billion years, that light has been traveling, its wavelength stretched by the expansion of space from brilliant, white-hot light into the cool, invisible microwave part of the spectrum. Today, this ancient radiation fills all of space, a constant, faint hiss with a temperature of just 2.7 degrees above absolute zero. In the 1990s, a NASA satellite called the Cosmic Background Explorer, or COBE, made the first detailed map of this radiation. It found that the CMB was astonishingly uniform in every direction, confirming the cosmological principle on the grandest of scales. But COBE also found something else, something crucial. It detected tiny, almost imperceptible variations in the temperature of this ancient light. Fluctuations that varied by only 1 part in 100,000. These were not random noise. They were the primordial seeds of all cosmic structure. The slightly hotter, denser spots were the seeds of gravity that would eventually grow into the vast clusters of galaxies we see today. The slightly cooler, less dense spots would become the great cosmic voids. This discovery was a monumental achievement, but it was just the beginning. These tiny fluctuations held the key to measuring the geometry of the universe. Scientists knew that the apparent size of these hot and cold spots on the sky would depend on the path the light had traveled over 13.8 billion years. If the universe were flat, the light would travel in straight lines, and the spots would appear a certain, predictable size, about 1 degree across our sky. If the universe were closed and positively curved like a sphere, it would act like a magnifying lens, and the spots would appear larger. If the universe were open and negatively curved like a saddle, it would act as a demagnifying lens, and the spots would appear smaller. The hunt was on to map these spots with enough resolution to measure their size. This led to 2 more generations of space telescopes, the Wilkinson Microwave Anisotropy Probe, WMAP, and later the European Space Agency's Planck satellite. These missions were feats of engineering, designed to measure temperature differences of millionths of a degree. They were, in essence, cosmic archaeologists, sifting through the afterglow of creation for the answer to one of humanity's oldest questions. And as the data from Planck came down, the picture became clearer than ever before. The spots were, on average, 1 degree across, the universe to the very limits of our observational power. was flat. The Planck satellite delivered the most precise measurement of cosmic geometry ever made. Its verdict, that the universe is flat with a margin of error of less than 0.5%, was a triumph of modern science. But in science, a precise answer often opens the door to even more subtle and difficult questions. Is the universe perfectly flat and therefore infinite? Or is it just so stupendously large that its curvature is too gentle for even Planck to detect? Imagine an ant on the surface of a giant balloon the size of Jupiter. The balloon is clearly curved, finite, and unbounded. But from the ant's perspective, its local patch of the surface would be indistinguishable from a perfectly flat plane. This is the situation we may find ourselves in. Our universe could be a closed, finite hypersphere, but one so vast that the 93 billion light-year observable portion is just a tiny, seemingly flat patch on its surface. To find this subtle, large-scale curvature, we need a new strategy. We need to go beyond the CMB and create a different kind of map. The hunt is now shifting from mapping the infant universe to mapping the adult universe. The new tools are not space-based microwave telescopes, but massive ground-based observatories designed to create the largest three-dimensional maps of the cosmos ever attempted. This new phase of the hunt is focused on measuring something called baryon acoustic oscillations, or BAO. The name is complex, but the idea is beautifully simple. In the early plasma-filled universe, sound waves rippled outwards from dense spots. These were not sound waves in air, but pressure waves in the primordial soup of matter and light. When the universe cooled and the CMB was released, these sound waves were frozen in place. They left a subtle imprint on the distribution of matter, a preferred distance between galaxies. It's as if the Big Bang sent out ripples in a pond, and the galaxies today are most likely to be found on the crests of those frozen ripples. This creates a standard ruler that is etched into the very fabric of the cosmos. We know the physical size of this ruler from our CMB measurements. It's about 500 million light-years across. By observing the sky and measuring the apparent separation of galaxies, we can see how this standard ruler appears at different distances and in different directions. By comparing the apparent size to the known physical size, we can perform a new, independent test of cosmic geometry on a scale that dwarfs even the CMB. This is the primary mission of a new generation of cosmic cartographers. Instruments like the Dark Energy Spectroscopic Instrument, DESI, are currently mapping the positions of tens of millions of galaxies. And soon, the Vera C. Rubin Observatory in Chile will come online. This revolutionary telescope will survey the entire visible sky every few nights, cataloging billions of galaxies and creating a cosmic movie of unprecedented scale and depth. It, along with future space telescopes like the Nancy Grace Roman Space Telescope, will map the BAO signal with incredible precision. This is the next frontier. It is a brute force approach, a high-stakes race to survey the cosmos with enough volume and accuracy to see if the parallel lines of the universe truly stay parallel, or if over billions of light-years, they begin to curve, betraying the finite, hidden shape of a universe that wraps back on itself. The quest to determine the shape of the universe is more than a matter of geometry. The answer, whether it be finite or infinite, has profound philosophical implications that reach far beyond the realm of physics. It forces us to confront our place in the cosmos and the very definition of what it means to be significant. For the past 500 years, the entire trajectory of science has been guided by a powerful idea known as the Copernican principle. It began with Nicholas Copernicus, who dared to suggest that the Earth was not the center of the universe. This was not just an astronomical reshuffling. It was a philosophical demotion. We were no longer the focal point of creation, and the demotions kept coming. We learned our sun is just an average star, tucked away in a quiet spiral arm of a typical galaxy, the Milky Way. We learned our galaxy is just one of hundreds of billions within our observable horizon. And we learned that horizon is likely just a tiny fraction of a much larger, perhaps infinite reality. The Copernican principle became a core tenet of scientific thought. We are not special. Our location, our planet, our star, our galaxy, none of it is privileged. But the two leading answers to the question, does space end, put this principle on trial in very different ways. Let's first consider the finite but unbounded universe, the elegant three-sphere that wraps back on itself. In one sense, this model upholds the Copernican principle perfectly. A hypersphere has no center and no edge. Every point on its surface is geometrically equivalent to every other. There is no special location. And yet, in another more subtle sense, it challenges it. If the universe is finite, then it is a singular, specific object. It contains a finite amount of matter and energy. There is a definite, countable number of stars and galaxies. Our cosmos is not an endless, homogeneous sea. It is a particular thing. This might reintroduce a sense of cosmic uniqueness. Our universe, with its specific laws and its precise amount of stuff, is all there is. It could be seen as a grand, self-contained cathedral. While we may not be at its center, we exist within a structure that is, by its very finitude, special. It is the one and only universe. Now consider the alternative, the infinite multiverse born from eternal inflation. This model represents the ultimate, and perhaps final, victory of the Copernican principle. It is the ultimate demotion. It suggests that not only is our location in space not special, but our entire universe is not special. Our whole cosmos, all 93 billion light-years of it, with its specific laws of physics, its particular arrangement of galaxies, and its capacity to harbor life, is just one bubble among a potentially infinite number of others. In the multiverse, there could be universes with different laws of physics, different fundamental constants, universes that are empty and dead, and universes filled with wonders we cannot even imagine. Our existence is no longer a profound feature of a unique cosmos, but the result of a cosmic lottery. We simply happen to live in one of the bubbles where the conditions were right for us to exist. This is the Copernican principle taken to its absolute extreme. It posits a reality so vast and so varied that our entire universe is rendered cosmically mundane, an insignificant footnote in an infinite library of creation. The choice between a finite cosmos and an infinite multiverse is a choice between two different kinds of significance. Are we part of a singular, special creation, or are we simply one of an infinite number of cosmic accidents? This ultimate demotion, the vision of our universe as a single, mundane bubble in an infinite multiverse, can feel like a descent into a philosophical abyss. If the cosmos is truly infinite, filled with an endless number of galaxies, stars, and even copies of ourselves living out every possible variation of our lives, what meaning can any single existence hold? If every achievement, every act of love, every moment of discovery is replicated an infinite number of times across an endless expanse, does that not devalue it? This is the existential weight of infinity. It threatens to dilute our sense of purpose into nothingness. For centuries, humanity has derived meaning from a sense of uniqueness, from the idea that our lives are singular events in a finite history. The infinite cosmos, in its most extreme form, seems to strip that away, leaving us adrift in a sea of cosmic redundancy. It can evoke a sense of profound loneliness, not the loneliness of being alone in the universe, but the loneliness of being cosmically insignificant. And yet, many scientists and philosophers who confront this staggering vision do not find despair. They find a different, more profound source of meaning. The significance of humanity, in this view, comes not from being at the center of the cosmos, or from being a unique creation, but from our capacity to understand it. The universe, whether finite or infinite, is vast and complex. For billions of years, it expanded and cooled, forged stars and galaxies, all in silence, with no part of it aware of the grand drama unfolding. Then, on a tiny speck of rock orbiting an unremarkable star, a part of the universe woke up. Matter, forged in the hearts of long-dead stars, organized itself into conscious beings capable of looking out at the rest of the cosmos and asking, "What am I?" We are, in the poetic words of Carl Sagan, the universe's way of knowing itself. This perspective recasts the entire quest for meaning. Our significance is not something granted to us by a privileged position in space, but something we create through the act of inquiry itself. The fact that a collection of atoms can piece together the story of the Big Bang, that we can measure the echo of creation, and that we can even conceive of ideas as strange and wonderful as a finite, unbounded universe or an infinite multiverse, is the true miracle. The meaning is not in the answer, but in the question. The mystery of whether space ends becomes a mirror, reflecting our own innate, unquenchable drive to explore, to know, and to push the boundaries of our own understanding. Whether we live in a single, self-contained cosmic cathedral or a single bubble in an infinite sea, our purpose remains the same: to be the witnesses, to be the part of the universe that looks back and marvels at the whole. In this view, our existence is not rendered meaningless by the scale of the cosmos, but is made infinitely precious. We are the custodians of its story, the consciousness of the void, and our fleeting lives are the brief, brilliant moments when the universe itself gets to experience a sense of awe. Our journey began with a simple, almost childlike question: does space end? We started under a comforting, solid sky, a celestial ceiling that gave us our place in the cosmos. We felt secure in our cosmic home, a fishbowl with defined edges. Then science began to tap on the glass, A man with a telescope revealed that the smudges in the sky were not clouds, but entire universes of stars. And in a dizzying instant, our home expanded beyond all reckoning. Then he showed us that these universes were all fleeing from us, that our entire cosmos was expanding, born from a single point in a distant past. The shattering of our cosmic fishbowl was complete. The ceiling was gone, replaced by the terrifying and exhilarating prospect of an open sky. We were forced to confront the boundary, not as a wall to be found, but as a paradox to be solved. An edge seemed to demand a beyond, a concept that crumbled into logical dust upon inspection. And so we turned to geometry, to the beautiful curved spacetime of Einstein, which offered us an escape. Perhaps our universe was a grand cosmic sphere, finite in its volume but without any edge to fall from, a place where a straight line, followed long enough, becomes a circle. This elegant vision, a single self-contained jewel of a universe, competed with a vision even more strange and vast. A theory born from the explosive birth of our cosmos suggested that our universe is not unique at all, that it is but one bubble, one island of calm in an eternally raging ocean of creation, a multiverse of infinite possibilities. The human story of this quest became as important as the science, a drama of intellectual titans, from the theorist who bent his own equations to fit his intuition, to the quiet observer who let the light of distant galaxies correct him. It became the story of young mavericks who, in moments of spectacular realization, dared to propose ideas that sounded like fiction, and then fought for them with the conviction that the universe is not only stranger than we imagine, but stranger than we can imagine. Our hunt for the answer led us to build magnificent tools, instruments designed to capture the oldest light in the universe, the faint microwave echo of the Big Bang itself. We learned to read the secrets in its ancient glow, to measure the shape of space by analyzing the size of primordial ripples frozen in time. And after all this, where have we arrived? We find ourselves standing on a precipice of understanding. Our best evidence points to a flat universe, a result that tantalizingly suggests a simple, straightforward infinity. Yet we know our measurements may not be the final word. We may simply be inhabitants of a universe so colossal that its true, curved, and finite nature remains hidden from us, just over our cosmic horizon. We are left with two profound possibilities. Either we live in a single, finite, but unbounded cosmos, all that is, and all that ever will be. Or we are a part of something immeasurably larger, a multiverse where our entire existence is just one of an infinite variety of cosmic expressions. We may never have the final answer. We may never be able to send a probe beyond the observable horizon, or receive a signal from another bubble universe. But perhaps the goal of this journey was never to arrive at a simple yes or no. Perhaps the true purpose of asking the question, does space end, is to continually expand the boundaries of our own minds. The question itself is the engine of our curiosity. It pushes us to build better tools, to dream up bolder theories, and to see our own existence in an ever-widening context. From a closed-in valley to a mountaintop, the view changes everything. The journey from a closed, finite sky to a potentially infinite reality is the greatest mountaintop we have ever climbed. And from here, we are left not with the comfort of a final answer, but with something far more valuable, a profound and unending sense of awe.